right. So this chapter is all about chemical bonding. The first section is just an introduction on bonding, what it is, why it is, what the different types are, and how you can identify which type of bonding you have. And as we go through this chapter, we'll be looking at each, okay, why is it? Can't find my mouse button. We'll be going through each type of bond. So like covalent, ionic, metallic, and then the last part is going to be on something called Lewis structures, which are used to help understand how bonding is done. And the last thing is going to be on VSEPR, which is valence shell electron pair repulsion, which is the rules that we use to try to identify the shape of the molecules, like the three-dimensional shape. Okay. Right, that's everybody. Cool beans. So again, today is just going to be an introduction. So I seriously doubt I'm going to take the entire period to do it, but that's fine by me. So a chemical bond is a mutual electrical attraction between the nuclei and valence electrons of different atoms that binds atoms together. So it's going to be either the, no, not either, but it's going to be the nuclei of one atom and the valence electrons of another atom. So the big question is why? Why are atoms bonded together? It all has to do with potential energy. As independent particles, atoms are at a relatively high potential energy, but nature favors arrangements where energy is minimized. So the general rule about just how the universe works is that potential energy, or just energy in general, a lower energy is favored, which means like any kind of state or process that reduces the potential energy of substances is going to happen over those that don't. The other thing that nature favors is disorder. So, for example, let's see, how do I explain this? So, if lower energy is favored, then you might think that endothermic processes would never happen, because an endothermic process is a process where energy is added. And so you would think, okay, well then endothermic processes can't happen naturally because obviously we want more, so we want less energy. But the truth is that endothermic processes do occur naturally, and melting ice is one of them. So ice only melts when energy is added to it, right? Because ice obviously has to be below 0 degrees. But once you are above 0 degrees, the ice starts to melt. That is an endothermic process. So why does it happen naturally if you have to add energy to it? And that is because of the disorder. So as ice is melting, the atoms become more disordered. You're going to learn more about that and what those particular things are called next year. But to understand why atoms bond, we look at potential energy of individual atoms. So most atoms are less stable by themselves than they are when they are combined with another atom. So by binding with each other, atoms decrease in potential energy, thereby creating a more stable arrangement. And that's the bottom line, is that a lower energy is more stable. Now, a bond includes valence electrons that are rearranged to make an atom more stable. The way the valence electrons are rearranged depends on the type of bond. So we have ionic bonding, which is when one atom loses an electron or more than one electron. Another atom will gain those electrons, and therefore they form ions, and the ions have a positive and negative charge. Positive and negative attract, and so you have an ionic bond formed because of the charge on the ions. Then you have covalent bonds are when electrons are shared between two atoms. Now, of course, we know based on polarity, the polarity of water, that in a covalent bond, electrons aren't always shared equally. But in a purely covalent bond, electrons are shared equally. So an example might be any diatomic molecule. And I'll talk about dipoles and the direction of poles later on in the chapter. So then the question becomes, okay, how do you know if a bond is going to be ionic or covalent? Now, it's interesting because when we usually teach this to, say, like somewhere in grade 7, 8, 9, we usually describe bonds as either ionic or covalent. But now that you're in grade 10, I can actually explain to you based on electronegativity, because we know what that is, that it's not really a question of black and white. It's a degree. So bonding is not really purely ionic or purely covalent. It really depends on how strongly the atoms attract electrons. And so most bonds fall somewhere in between ionic and covalent. So we have to refer back to electronegativity, which we studied in the last chapter, which is an atom's ability to attract electrons. And I should add in a compound. It's a very important point to add because electron affinity is an atom's ability to attract electrons when it's by itself, but in a compound, it's electronegativity. So the degree of bonding between atoms of two elements being ionic or covalent, we estimate that by calculating the difference in the electronegativity of these two elements. So we have this kind of graph, I guess. And you can see on the left-hand side, this is the difference in electronegativities between the two elements in the compound. And so if you are between 0 and 0.3, then that's considered a nonpolar covalent bond. If the difference in electronegativities is between 0.3 and 1.7, that is considered a polar covalent bond. And if you're between 1.7 and 3.3, that's considered ionic. On the right-hand side, they have what they call percentage ionic character. And we don't usually refer to this side necessarily. That doesn't mean you'll never come across a question about it, but it's basically just like saying, on a scale of 0 to 100, how ionic is this bond? So 0 to 5% ionic is nonpolar covalent, 5 to 50 is polar covalent. Sorry, I got bad sleep last night. And 50 to 100% is considered ionic. But again, in general, we go by these ranges. Oops, I'm gonna take that all the way down. Go down to those ranges. So here's an example. Fluorine's electronegativity is 4.0. Okay, we know that because it's been given a random assignment of a value of 4, and all of the other elements are compared to fluorine. Cesium is 0.7. So if you have a compound that is made from cesium and fluorine, you would subtract these two numbers. You would say the difference in these two numbers is 3.3. So it is 100% ionic. Okay, that would be 100% ionic bond. So the greater the difference in electronegativities, the more ionic the bond is. And again, you can kind of very loosely go by position on the periodic table. If you have two elements that are pretty close together, especially around fluorine, because the nonmetals have a tendency to form compounds together, you can pretty much rule out that they're going to be ionic because they're close together. But if you have something, say, from group 1 and group 17, they're on opposite sides of the periodic table, so you can relatively intelligently guess that it's going to be an ionic bond. The bonding between atoms with an electronegativity difference of less than or equal to 1.7 has an ionic character less than or equal to 50%. So basically that just means if you are 1.7 and below, your ionic character is below 50%. And that is where covalent bonds begin to be classified. Now, whether or not you're polar covalent or non-polar covalent will depend on how far down below 1.7 you become. If you have atoms of the same element, that is going to have an electronegativity difference of 0 because it's the same element. So they're going to have the same En. And so that's going to be 100% purely non-polar covalent. So for example, 2 hydrogen atoms, they're going to, I don't know offhand what the electronegativity of hydrogen is, but let's just say it's 1.5. I don't know what it is, but we'll just make it up. So if this hydrogen is 1.5, this hydrogen is 1.5, 1.5 minus 1.5 is obviously 0. So when it comes to that graph, which I don't have here, it's all the way down here, 0% ionic character. So that's purely non-covalent. Okay. So again, the diatomic hydrogen, sorry, has a 0% ionic character. So it is considered a non-polar covalent bond, a covalent bond in which the bonding electrons are shared equally by the bonded atoms, resulting in a balanced distribution of electrical charge. This is important because if electrons are shared equally, you don't have this partial charges that you do with polarity. And then that's why it's a non-polar covalent bond. Because if you remember back from the beginning of history, when we looked at water as a molecule and the bond between the oxygen and the hydrogen in water. No, I did not get enough sleep today. That's why I keep yawning. Sorry, I just looked at the chat. So, oh yeah, when we started looking at the bonding in water, the difference between oxygen and hydrogen, back then, I told you that it's because electrons are more attracted to oxygen because they have more protons in the nucleus. That's not exactly accurate, but you didn't know about electronegativity back then. So that's how I explained it. But now we know it's based on electronegativity. Oxygen is very close to fluorine, so it's going to have a relatively high electronegativity. And then hydrogen, of course, is all the way on the other side. So there's a large, but not so large it's ionic difference in En. And so you end up with polarity because this unequal sharing of electrons leads to partial charges at different ends of the compound. So an En difference of between 0 and 0.3, you would classify that as a non-polar covalent bond. And I'm not going to expect you to memorize all of the En values. I will give you a list if I ask you to classify them. So then the next category up, we look at polar covalent bonds, bonds that have significantly different electronegativities. The electrons are going to be more strongly attracted to the more electronegative atom, which is going to be the atom that is closer to fluorine on the periodic table. These bonds are called polar. They're called polar because they have an uneven distribution of charge, and they have an uneven distribution of charge because electrons are not shared equally. They're not shared equally because the electronegativities are different. So you have higher En means electrons shared unequally, which means you have partial plus and minus charges. That's a horrible, I think it's gamma, whatever. Partial plus or minus charges, which means you are polar. So it's really important, especially when we were talking about like critical thinking and logic skills and reasoning and things like that, that you are able to make linear connections. So like if A equals B and B equals C, then A equals C, that kind of thing. So you have an element that has a higher electronegativity. That means electrons are going to be more attracted. I should actually miss a step here. Electrons more attracted which then leads to electrons being shared unequally, which leads to positive and negative partial charges, which leads to polarity. And then, of course, when it comes to water, polarity is going to lead to many other properties like hydrogen bonding, cohesion, adhesion, and temperature moderation, which we studied in biology already. So here's an example of hydrogen and chlorine. So chlorine is right underneath fluorine. It's going to have a higher electronegativity, which means electrons are more attracted to chlorine than they are to hydrogen, which gives, try to get the writing out of the way. Okay, which means that the chlorine side is going to have a partial negative charge, and the hydrogen half is going to have a partial positive charge, leading to a polar bond. So this is for a difference in electronegativity of values between 0.3 and 1.7. Again, remember, it's the difference in electronegativities. And so between 0.3 and 1.7, you're going to have between 5 to 50% ionic character. Again, I usually focus on the electronegativity difference. Okay, what's the point of that blank diagram? I don't know. I guess just showing, no, because that's the hydrogen, that's the electron cloud. I don't know. I don't know what the point of this diagram is. Oh, because I'm going to put in partial positive, partial negative. Excuse me. All right, so let's look at an example. Using electronegativity differences to classify bonding between sulfur and the following elements: hydrogen, cesium, chlorine. In each pair, which atom will be more negative? So here I've got, we've got sulfur, which has, I don't have the listing, but it's probably in your book anyway. Sulfur is 2.5. So we've got hydrogen is 2.1. That's on electronegativity, an EN. It's an EN difference of 0.4. That puts it, let's see if I could put that chart up again. So we have, put on further. We have 0 to 0.3, 1.7, 3.3. Okay, those are our values. So this is non-polar covalent. And then we have polar covalent, ionic. All right. So if 0.4 puts us just above the non-polar into the polar, so it's a polar covalent compound, and the more electronegative atom is sulfur. So if you have hydrogen and sulfur, the electrons are going to be more on this side. So that's going to have the negative, slightly negative charge. Then you have cesium. Cesium's 0.7. That gives you an electronegativity difference of 1.8. That puts you above here in the ionic category. And then finally, chlorine. Chlorine is 3.0. That's a difference of 0.5, which again puts you down in this polar covalent area. But now chlorine is the more electronegative element. Let me get out. Do they have the values is the question. Here. I'm looking on page 167 if you've got your book out at all. It says using electronegativity differences in figure 1.2. So you'd have to go back to chapter 5 to find that chart, which had properties. Here we go. Is this it? No, that's electron affinities. Radii. There we go. So if you go to the chart on page 153, that gives you your electronegativity differences. So we're going to look at chlorine versus Ca, chlorine and oxygen, chlorine and bromine. All right, so looking at, and you don't have to if you don't want to, but I've got it here. The value of chlorine is 3.0. And calcium is 1. Okay, oxygen is 3.5. Bromine, 2.8. Okay, so these are our EN values. So if we're going to analyze a compound formed between calcium and chlorine, we have to do 3.0 minus 1. So 3.0 minus 1.0, that's 2.0. That is ionic. The more electronegative atom is chlorine. Then you go to the next one, chlorine versus oxygen. Oxygen actually has a higher EN than chlorine. It's 3.5 instead of 3. Sorry again. That's an EN difference of 0.5, which puts you in the polar covalent. I'll just call it P-C. Polar covalent. And this time, oxygen is the more negative atom. And finally, you have chlorine and bromine. So that's 3.0 minus 2.8. That is 0.2. And that puts you below the polar covalent into the non-polar covalent category. And again, chlorine is the more negative atom there. Okay, so again, we've got ionic between calcium and chlorine, which makes sense because calcium is on the left-hand side of the periodic table, chlorine is on the right-hand side. And these two also make sense because these are also very close. They're all really close together. So it makes sense that they would be in the covalent range. Okay.